Okay, so hi everybody. Welcome to our weekly meeting. Today is with great pleasure that I will introduce Gabriele Bruni. So Gabriele is a dear friend of mine, and he nicely accepted our invitation to give a talk today. So Gabriele got his degree at the University of Turin in 2008. And then he moved to Bologna for a PhD on broad absorption line quasar at INAF IRA at the Institute of Radio Astronomy in Bologna. Then after some years of postdoc experiences at IRAM in Granada and in the VLBI group of the Max Planck Institute for Radio Astronomy in Bonn. Then finally in 2017, he joined the integral group at INAF IAPS in Rome. So he went back to Italy. And he's now an ESA Discovery Program Fellow. His research focuses on accretion, ejection processes on compact objects, and in particular, the launching of jets and the winds in active galaxies. So thanks, Gabriele. Now the floor is yours.
Thank you, Carolina. Everybody, it's a pleasure to give a seminar. I want to show you some of the main results from this project that we've been working on for the past more than 5 years now. We try to study giant radio galaxies selected at high energy because we had some initial indication that these galaxies were more abundant in hard X-ray catalogs like the one done by Integral and Swift over years. So we are now in a position where we have more than 20 years of data collected by these missions, and we can study populations and cross-match these sources and catalog with the new generation radio surveys that are covering the opposite end of the electromagnetic spectrum, giving us indication nevertheless on the same processes that are non-thermal processes in AGN. So today I will try to reassume some of these results, starting from a few basic concepts that we will find along the slides that you already know, of course. When we talk about jets, we don't talk only about blazars and AGN, but we know that we can find jets also in stellar black holes, X-ray binaries. So the kind of physics behind that is really scale invariant. You can find relativistic jets launched by different masses of black holes at different accretion and with different magnetic fields. Anyway, you still need three main ingredients to form jets. That is some material accreting on the black hole, the magnetic fields that threads the plasma and allows you to collimate and launch the jet, and the spin of the black hole. The three of them are necessary and are found at different scales. One of the most dominant effects is the accretion rate that can be used to distinguish between low accreting systems when we are below 1% of the Eddington rate. And this gives you a radiatively inefficient regime called also jet mode. While if you have more than 1% of the Eddington rate, you can have a radiatively efficient regime with a very powerful accretion disk and a corona. So we will keep in mind this latter concept for the kind of AGN that we are studying with these projects. But a few more concepts that are useful when you are studying black hole are the different scales at which you can see this phenomenon. If we consider AGN in this slide, you can see that the jet scale starts from the neighborhood of the black hole where there is the launching region. Then at about 1 parsec, you can have the acceleration and collimation region that is the subject of many studies in the VLBI field. And then you enter the ballistic, the kinetic flux-dominated part of the jet, where the jet can expand up to hundreds of kiloparsec, and in some cases also megaparsec. until it reached dissipation because of the interaction with the intergalactic medium. So it gets it's not collimated anymore, and it forms these characteristics lobes and bubbles of plasma, and then can have very complex morphologies, as you can see on the left, due to the buoyancy of this plasma in the surrounding medium. So you can study very different scales in several magnitudes, order of magnitudes in the physical scale. And in the last years, there were some developments. I will talk about radioastron because I'm a radioastron aficionado and I could contribute to the mission, but there have been also many other results. In particular, for radioastron, it was possible to study the transversal structure of the jet. So radioastron was a mission orbiting Earth and reaching almost the moon when it was at apogee. And such a long baseline together with Earth radio telescope allow us to reach micro-second resolution in the centimeter band, in the gigahertz domain. So we could really resolve transversally the jet, as you can see in the top image, at frequency where it was usually not possible, and separate the different components of the jets that are a central spine that is more powerful and more fast, and an external layer that is called the shear, where the plasma is lower and is interacting with the medium. So you can have these two regions that can be very useful when you want to model the multi-wavelength emission of the jet. So you can suppose that different region contributes in different wavelengths. And in this way, it was possible to model the emission up to gamma. Also, these characteristic helical filaments that was found in another radioastron paper by Antonio Fuentes confirmed that actually the magnetic field should thread the jet in such a way that it preserves collimation for kiloparsec, okay? So here we are studying the very central part, the very inner part of the jet, but we can assume that these filaments are present on a much larger scale, as seen more recently with the VLB observation of M87 by Alice Pazetto et al. That was connecting very nicely with these filaments that we see on the parsec scale. So this helical structure of the magnetic field is supposed to be due to the spin of the black hole that contributes threading the space-time and helical magnetic fields. Another important result just a couple of years ago was the one by your colleague Ioannis Liodakis with the IAPS mission that could confirm the paradigm that we were believing in for the past 30 years, that is the shocking jet paradigm, and confirming that these shocks, these standing shocks, can produce electromagnetic emission at different wavelengths, up to high energy, up to X-rays, and very nicely agree with the view that we had so far about the presence of a VLBI core that is a standing shock along the propagation of the jets. So this was a zoom in the very inner regions of the jet, but allowed us to understand the very basic concepts at the origin of this incredible phenomena. So when I started this project, I tried to put down the main question that we still have about jets. Of course, are very broad and very complex, but at least we should try to give some answers to some of the points. So these are probably the three main questions. How jets are triggered and restarted, because we have seen now in many sources that the radio phase, the jet, is an episode along the life of the AGN. It's not always present. You can have even a duty cycle that you can try to estimate that gives you the percentage of activity of the jet with respect to the total lifetime of the AGN. and we could do that for at least one source so far. Then another important question is how the jet evolve in the intergalactic medium. What's the dynamic of the jet? So it's necessary to collect observation at very different scales with respect to VLBI if you want to have a bigger picture about how these jets impact the medium and can have a role in the evolution of the universe. Very recently, there was a result that I will show you in a couple of slides about Oei et al. Published on Nature, showing the biggest ever giant radio galaxy that reached 7 megaparsecs. So it's really out of question that jets can have a role in the evolution of the large-scale structure of the universe. And finally, as I said before, what's the jet duty cycle? Why the duty cycle is so important? Because if the jet is episodic in nature, then you can study how it impacts the host galaxy. So not only the very large scale, but also the influence that can have on the plasma compression, star forming region inside the host galaxy. And this is related to the duration of the jet phase. Okay, so all of these are important at different scales, but why did we start with high energy radio galaxy? We know that radio galaxy in high energy catalogs are only a smaller fraction. For example, if we look at the integral sample, AGN sample in the hard X-ray band, they are only 8% of all these AGN. If we look in the Fermi catalog at GV energies, it's even less. It's only 1% because, as we know, Fermi sees mainly blazars, okay? So jets pointing toward us. But still, this little fraction can give us some very nice indication about the physics in jets and lobes, as I will show you later. In addition to radio galaxy that are present both in FR1 and FR2 geometries that are the classical division of the radio galaxy phenomenon, there is also a growing fraction of FR0 radio galaxy that are very compact radio sources that probably could not develop up to kiloparsec or megaparsec, but will still be the dominant population seen by SKA in the near future because they are far more numerous than classical FR1 and FR2. And these have been detected in gamma as well, as recent studies revealed. So they are also an important part of the high energy population. So despite these objects are quite rare in the high energy sky, they offer the possibility to study the relations between accretion and ejection and their connection. So we will concentrate mainly on two samples, the hard X-ray giant radio galaxies and the GV, that means Fermi detected radio galaxies. And to do so, we collected data from the recently released surveys in the radio band. Fortunately, in the past years, we have seen many new radio surveys that can go much deeper than before, much deeper than the classical first MVSS, WENS surveys, and they can cover a broad range of the radio spectrum. We have the LOFAR survey and TGSS survey at 150 megahertz that covers the very low frequency region where you can see the lobes extended on megaparsec scales, plasma that is already very relaxed and forms these clouds. And if you move to higher frequency, you can count now on RAX that has even a second frequency that I didn't put it here, that is 1.4 gigahertz, plus the VLAS surveys, that is the new survey by VLA and covers the 3 gigahertz range. So this gives us a taste of how SKA sky will be because they are going much deeper and higher resolution. And in particular, VLAS plus RAX, that is in the southern hemisphere, can cover the entire sky. That is really what you want when you are studying catalogs of objects by satellites that, of course, have no constraint on the position on the sky. So we put together these two that are more or less at the same frequency and same resolution. Sensitivity is also more or less comparable. They both go deeper than previous surveys at least. And we use this data to study this sample of giant radio galaxies selected by the Integral and Swift satellite. So just a few words about giant radio galaxies. As we discussed previously, the lifetime of a jet, of a radio source, starts with a very compact source that is below 1 kiloparsec and can be called GPS or CSS because of this typical peaked spectrum in the gigahertz range. Then when it expands, it becomes an FR1 or FR2. The distinction mainly reside in the dominance of the lobes or the inner part of the jet. And here the luminosity starts to decrease because the plasma expands and you have a lower surface brightness that makes them a bit more difficult to study. Then expanding even more than FR1 and FR2 and reaching the megaparsec scale, the giant radio galaxy can really have a size that goes up to the cluster size. And these are even more harder to study because of their even lower frequency and surface brightness of the plasma. So for these, LOFAR is especially good because it allows you to reconstruct the extended part of the emission. Finally, at the end of their lifetime, radio sources can have a dying core that is no more detected or barely detected in radio observation, but you can still see these expanded regions of plasma where emission at low frequency is still present. So this is the whole picture. And I will show you that more than one radio phase is present in our objects. So keep in mind the GPS phase and the FR2. And giants in particular are, let's say, conventionally defined as objects larger than 0.7 megaparsec. As I said, that they have a low surface brightness. Buoyancy can result in complex morphologies, so it's not always easy to have the right observation to discover them and study them. Historically, they were very few. If you look in the 3C catalogs, for example, they are only 1/6% of the entire radio population because they are so difficult to detect and to study. But thanks to LOFAR, and now we have hundreds of these objects that allow us to do, for the first time, a very nice population study and study how they can be present at different accretion regime, because don't forget that everything depends on this inner central engine that produces these jets. So what we want to understand is whether they are so big because the radio phase was so long that allowed them to reach these sites, or maybe the jet power is higher, allowing to carve a tunnel in the medium, the surrounding medium, and reaching these unparalleled distances. But most of all, they are also the ideal laboratory to study the jet duty cycle, because when you consider such a long radio phase, a radio structure that has been formed along mega years, is also probable that if jet is episodic, as we think, you can find another newborn jet in the center of this structure in the host galaxy. Okay, so let's see what we found. But first, I want to show you this very nice animation that has been produced for the Nature paper published just 1 month ago, a couple of months ago, by Oe et al. About the discovery of this giant radio galaxy that was a 7 megaparsec large. So it's really a record. Maybe it stopped. Let's try again. It's really a record, and the good news is that it's so big that it can fill the voids in the large scale structure of the universe. So you can see this web of a galaxy all around in the simulation, and the size of these jets is so big that it can connect two of these web stripes in the sky. So they can really contribute to the evolution of the universe, the plasma in the universe, and the magnetization of the universe. Okay, so our sample, as I said, was selected starting from Integral and Swift in the hard X-ray bands. So before I even arrived here, the group was already cross-correlating this catalog with MVSS, FIRST, SAMS, that are the old generation radio surveys, to see how many radio galaxies were present. So surprisingly, they found that 15% of the 22% of the radio galaxy were giants. That is 4 times the fraction that I showed you before, the fraction of radio galaxy detected in the previous radio surveys. So it seems to suggest that if you start from a highly accreting AGN, like the one selected by Integral and Swift, you can find more easily these very big radio galaxies. So, of course, when you think about the hard X-ray flux, you are intercepting radiatively efficient accretion mode. Okay, so the starting bias of this study was to pick up only those objects that have high accretion because they are so bright in the Integral and Swift sky, and they can be detected by them. Don't forget that these are missions by 20 years ago, so they are not the latest version, but still they can see the very bright sources. And when you select these objects and you cross-correlate them with radio surveys, you pick up FR2 because this leads to a high excitation radio galaxy selection. And we know that FR2 are more abundant in Hertz, high excitation radio galaxy. So that is why the initial fraction of giant radio galaxy was much higher, but still this gave us the possibility to study the presence of more than one radio phase in these objects, and then the duty cycle of the sources. When we talk about restarting activity in radio jets, there are mainly 4 indicators that can be used for to discover a second radio phase, in addition to the one that generates the large-scale lobes. You can have a double-double radio galaxy where 2 couple of lobes are present. So you can see one is more extended and is due to the previous radio phase, while the new one generates these inner couple of lobes indicated by the red arrow that give you a much younger age when you calculate the kinematic age. Another example is X-shaped radio galaxies that are basically double-double radio galaxy where the new jet has a different axis with respect to the previous one. So you can spot this X structure. Sometimes these sources can also be due to the backflow of plasma from the lobes that goes back towards the host galaxy, gets deflected, and generates this extended X shape. But in a few cases, you can also have a genuine X-shape due to a new radio jet. Another example of restarting activity is the presence of a radio cocoon that you can see in the lower left corner. That is this black region that enclose the entire lobes that can be seen at higher resolution, and it's kind of a fossil of previous radio phases. Okay, so when the jet stops, the lobes expand and can form this cocoon of plasma that surround the host galaxy and the new radio phase that you can see as the contours with the white contours that are the new lobes. Finally, another case of restarted radioactivity can be spotted when you see a GPS in the core of a radio galaxy, as you can see here. If you draw the radio spectrum of this central dotted that you can see, and that also includes the host galaxy, because the scale is so big that the host galaxy is just a dot inside that. You can see in the radio that there is a peak And this peak can be an indicator of a young radio jet that is self-absorbed and produce this typical peak indicators range. So with a single dish observation, we could spot some of these cases in our sources. They were 60% of our sample, more or less. We performed higher resolution images to confirm that it is actually a new radio phase, and I will show you an example in a few slides. And we could confirm that all of them are genuine GPS that are mini radio galaxy inside the radio galaxy, okay, a sort of a matryoshka. Okay, so in addition to these surveys that I was showing you at higher frequency, LOFAR can be really helpful in studying extended plasma regions. So we could take advantage of the LOTS surveys, that is the one by LOFAR at 150 megahertz. That has been performed so far only with the inner part of the array, but still there are data from the international stations that are the one you can see in the maps that encompass the entire European continent that can be processed to reach sub-second resolution at this very low frequency. And it's really groundbreaking because it has never been reached such a high resolution in low frequency radio band. So I'm looking forward to this reprocessing for select targets that will allow me to do even a better job. But for the time being, let's see what LOFAR can reveal about our giant radio galaxies. You can see this is one of the sources that were in the footprint of the survey. And you can see that we can spot both a very extended lobe on the left, an extended region on the right that is just below the hotspot that is called W1 that deserves more study to understand whether it's due to a previous phase or it's just a backflow from the hotspots W1. Then don't get confused by the other galaxy that is present in the field, that is two masks. You can see that on the top right corner. This is another radio galaxy that has nothing to do with this one, so you can ignore that. And in the inner part of these radio galaxies, you can see in the zoom images below, you can see there is a second radio phase that we can also see with LOFAR at the same frequency. And it is interesting trying to understand what's the age of this new radio phase with respect to the previous one and estimated duty cycle of this source. So I was lucky enough to have a master student working on that collected data at different frequency, trying to put a date on the lobes, on lobe A and lobe B and C, trying to get an age for this very old radio phase and compare that with the inner jets that are much younger. This is a complex work because you need to study the spectral curvature in the radio band for the different region of the lobes, as you can see here. So you need observation at different radio frequency, but with comparable resolution and with comparable sensitivity to the extended structure, that is the shorter baseline of your array. And it's not easy to get, but we could put together GMRT, LOFAR, RAX, that is actually the ASCAP interferometer in Australia, plus VLA observation in a compact configuration, trying to reconstruct this extended emission. And we could try to estimate the age of this plasma by identifying the breaking point in the spectrum. That is a sort of knee that happens when the plasma gets older and its energy goes down and contributes more to the low frequency than to the high frequency. And in this way, you produce this kind of knee in the spectrum, in the radio spectrum. So we could estimate an age for the lobes that range between 40 and 70 megayears. Is not so precise, but at least you get an order of magnitude. In any case, it's tens of mega years, okay? And you can compare that with the kinematical age of the inner part of the jets that can be deduced by previous VLBI studies by Giovannini et al. And we could understand that the younger radio phase should be around 12 mega years. The ancient one, as I said, is, let's say, more than 30 mega years. And in between, there is a void that it needs to be at least 27 mega years. Okay, so a quiescent phase where the jet was not present, was not propagating, and it lasted almost 30 mega years. So putting this information together and considering a total lifetime of 70 mega years, we can get a duty cycle of 60% of the jet, okay? So there are not so many sources with this kind of estimate so far, but we are in agreement with the other 2-3 sources with reasonable estimates. So we start thinking that this might be the typical duty cycle of the jet. So let me just get a bit of water. So this is another example of a giant radio galaxy from our sample that we could study with LOFAR. And in this case, LOFAR was the only instrument able to see these H1, H2 hotspots that are so collimated and on a different axis with respect to the actual lobes that suggests the presence of a fossil radio phase that produced this larger and fainter radio emission that we can see in this image. So this is so far the best candidate we have for jet precession or even reorientation if the new radio phase has a different axis and there is no precession. Nevertheless, a recent simulation of precessing jets are in very good agreement with what we see, because as you can see on the left, this work by Orton et al. Shows that if you give the jet enough time and you put a precessing angle in the simulation, you can successfully reproduce what we are seeing. It is a much wider couple of lobes that are fainter, plus an inner couple of lobes smaller and more bright. So we performed follow-up observation with VLBA on this source to see whether the inner jet on the parsec scale present an even different angle with respect to these two axes, these two yellow axes that you can see in the picture. And that are just under analysis because we observed past August. We really hope to see a precession. In the best scenario, this could be also a good candidate for a dual black hole. And so if this is true, this can be also a population for the next generation GW antennas like LISA and ET, because they will detect low frequency gravitational waves from couples of supermassive black holes. So maybe the radiomorphology can serve as an indicator of the presence of the dual black hole in the center of the AGN. Okay, but we need to demonstrate this before. So as I was saying, let's see what we get if we zoom into the newborn jet of this sample with VLBI observation. In particular, we could collect data from an EVN large project plus LBA, that is the Australian version of the EVN, and allow us to cover the entire sky. So when we talk about VLBI observation, if we go back to the question that I was discussing before about jets, with VLBI, we can mainly answer to the first question, that is how jets are triggered and restarted, and part of the second one, that is how they precess, and if there is or not a supermassive black hole system in their center. I will show you two cases of GPS that are a young radio phase in the core of a giant radio galaxy. In these two cases, we could zoom in with the VLBI observation, and as you can see, you can spot a mini radio galaxy with these very nice tiny lobes near the core. And this confirms that the GPS core we were seeing, the GPS spectrum that we were seeing with the Effelsberg single dish observation is really due to a compact radio phase that is developing in the core of these galaxies. So this will be the next one for the duty cycle estimation, because we know that GPS are almost 1,000 years old. So that this phase is very brief, very short, because after a few thousand years, the plasma is already so expanded that it does not present this self-absorption anymore. So you have just a straight power law, like the one you expect from classical radio emission. And so that we can really compare the age of this GPS phase with the megaparsec scale lobes that will be dated through the synchrotron aging that we have seen before. And this will be the subject of a future paper. We're trying to put together all the information we have. In some cases, where when you zoom into the core of these giants, you can see even more strange things, okay? You can see, for example, in this one, we zoom in, we see a similar structure in the middle image to previous observations by I mean, catalogs and calibrators catalogs. But if you zoom in at 22 gigahertz, that is almost 1 parsec resolution, you can see that the structure is symmetrical and it resembles the mini radio galaxy that I was showing you before. And indeed, we have a GPS spectrum, but the axis is very different from the previous axis that we can see on the megaparsec scale. It's almost 90 degrees with respect to the megaparsec scale lobes. This is not the only case we have in the sample. There is another source that we studied in detail that present an almost 90-degree reorientation of the inner jet. As I said before, these extreme cases can be also due to binary black holes, but it's really hard to spot them. And we have no evidence of binary black holes in these sources by other bands. We don't see, for example, in the optical band, two emission line separated by a few kilometers per second. We don't see any other indication that suggests the presence of a second AGN, a second black hole. But still, it's not easy to change the jet axis by so much, so many degrees. If you consider the momentum inertia that a system like that can have, you cannot just move the axis of a black hole by chance, okay? So it's not easy to understand what's going on in these objects. Okay, so I will conclude the part on the giant radio galaxy. After this, maybe Carolina can tell me how many minutes I still have, so I will decide how many slides to show you in addition to this. So we have
still 10 minutes at least.
10 minutes. Okay, perfect. Okay, grazie. So concluding the part about the restarting radioactivity in this giant radio galaxy, what we are doing now after discovering that almost all of these sources have a second radio phase is to understand if the hard X-ray selection has a role and produce a bias in the selection of these objects. So we compare this sample with a comparison sample selected from the radio and not detected in the hard X-ray catalog, so we can call it hard X-ray quiet, so to say, but it's not really quiet, of course. And we could verify through optical observations that this comparison sample is mainly composed by low excitation radio galaxies that are LERGs, while, as I said before, our sample is mainly high excitation radio galaxy, HERGs. And if you put these two groups of sources in the diagnostic plots, like the one you can build with wise magnitudes. That is very useful. You can see that they fall where lercs and ergs are expected to be. So we can confirm also through wise magnitudes, infrared magnitudes, that they are actually divided into ergs and lercs. Looking at the restarting radioactivity in this comparison sample, through the same indicators I was showing you before, that is GPS, radiomorphology, we could spot a similar fraction of restarted radio sources. And so this convinced us about the fact that it is not the accretion mode, okay, that plays a role in the jet evolution, because we know that ergs and lercs are in very different regions of the Eddington rate diagram, as you can see on the right. Lercs at a much lower accretion rate than ergs. And so you would expect this to have an influence on the jet evolution and the restarting radio phase, duty cycle of the jet. But apparently it's not, because we find a similar fraction of restarted radio galaxy. This is still in prep paper, but I'm quite confident about the results, and hope to discuss this more in the next months. Okay, so I want to conclude with an example of a radio galaxy detected by Fermi that is interesting because, as we were discussing before, Fermi sees mainly blazar, because of course jets pointing toward us are much more brighter in the gamma ray than other misaligned AGN. So this little fraction of misaligned jets has been studied along years, and the statistics is increasing. But it's very important to understand them to see where the gamma ray emission is produced. So there were some work at the beginning of the Fermi observation by the Fermi collaboration that studied, for example, the two biggest radio galaxies that we have in the sky, that are Centaurus A and Fornax A. In particular, for Centaurus A, Fermi can spatially resolve the lobes from the core. So what you can do is to see how much of the gamma ray fraction emission comes from the lobes instead from the inner part of the jet. So a first modeling of this emission in the lobes was performed by the Fermi collaboration, but this was implying a very high proton energy density in the lobes to reproduce the gamma ray flux that we see with Fermi. So there was a recent series of paper by Persich et al. Trying to remodel this emission on the basis of inverse Compton of the ambient photon field. Okay, so inverse Compton of the electron presence in the plasma populating the lobes, forming the lobes, of the inverse Compton of the ambient photons due to the host galaxy and CMB, but mainly host galaxy, because it provides you with photons in the optical band that can be sufficiently upscattered to gamma ray energies. Okay, so they could model this gamma emission without the necessity for protons. That is very important, because you don't expect many protons to be present in the lobes, because as we know, proton mass is much higher than electron mass, and you don't expect to accelerate them to relativistic energies like you do for electrons in jets. So if jets are mainly populated by electrons, you ask yourself how you can end up with protons in these lobes. Okay, so it was a bit improbable to have such a high proton energy density. But through this new remodeling, it was possible to explain this gamma ray emission from the lobes. So we found this radio galaxy among the integral AGN, again, because we start from the high energy sky in any case. We could spot this one thanks to the new generation radio surveys that I was mentioning, in particular with RAX at 800 megahertz. You can see the extended structure of the lobes. and a bit of backflow, that is the peak you can see towards the north. While if you zoom in with VLAS at a higher resolution and slightly higher frequency, you can really separate the lobes from the cores, okay? So we performed the ATCA observation because it's quite a southern source at -32 declination. So with ATCA, we could also observe lobes and the core at higher frequencies. And we could build the SED, the broadband SED of the lobes and the core separately, okay? So what you can see here is a gray line that indicates the template you can get from 3C273 that gives you the expected emission in the gamma ray band after you normalize that for the core emission, that is the left part of the graphic where you see those blue points, okay? So the blue points are the core only emission in the radio, while the orange points are the lobes emission. And if you normalize this 3C273 template to the core emission in the radio, you can estimate how much gamma ray emission is expected in the Fermi bands, okay? And as you can see, the gray line falls almost 1 order of magnitude below the flux that a Fermi measured for this source. That is the blue line, okay? So there was this gamma excess that we could not justify with the core, because as we have seen, the jets apparently stay on the plane of the sky. So we don't expect much gamma emission like you see in Blaser, okay? So we perform a modeling using the model by Persich et al. That, as I said, accounts for the JEV emission on the basis of inverse Compton on the photon fields. And we could successfully reproduce the JEV emission from the lobes that Fermi measure, okay? So you can see these tags on the SED that indicates lobes and corona plus lobes, because that's the hard X-ray range where integral can measure very nicely the emission from corona. There is also a contribution from lobes, but is just below the corona, the one expected by the corona that dominates these bands in misaligned AGN. So this indicates that more of these objects might be present in the high energy sky once SKA and GVLA will start looking at the sky at higher sensitivity than nowadays telescopes. And these are examples of other radio galaxy with Fermi counterpart that we could spot simply looking at the data in the nowadays surveys, okay? So we expect there will be more and more of these sources populating the high energy sky. And this gives us some new insights in the physics of the gamma ray production in the lobes that are populated by very relaxed plasma. To do so, we already proposed to join the Meerkat Plus survey that will start probably this year, and uses the precursor of SKA in South Africa. That is already 68 antennas, and we'll try to observe deeper and deeper at 3 gigahertz. So this would allow us to spot more of these objects. And I think I can leave you with the summary and skip the neutrino part because there is no time. So this is the summary, and thank you very much.
Thanks, Gabri. Thank you very much. Very interesting topic and talk. Thanks.
Welcome.
So let me see. Any question? You can unmute yourself. Okay, we'll start then maybe with one. So, so I understand that for these giant radio galaxies, so it's still on doubt if it is that they had much more time that normal radio galaxies to expand that far, or if that it is that their jets are more powerful, right? And they have more efficiently pass through. Since you did this work with the master student on this giant radio galaxies, and you measure the lifetime and the duty cycle, right? You have an estimate of the lifetime of the. So I guess my question is a two-folded question. So from the side of the lifetime and duty cycle, how does this compare, the one you measure for this source, the lifetime and duty cycle, how does this compare to lifetime and duty cycle in other radio galaxies that are not so giant, FR2 radio galaxies? Do you have an idea? Because I don't know.
Yeah, well, the other couple of objects that were studied with such a technique are also very big radio galaxies. They are not giants, but they are anyway in the range of mega years activity. So we are not yet in the position to compare giants with normal radio galaxy because we need much more statistics. But anyway, you can see the final estimates here are more or less what you can find also in other radio galaxy because the uncertainty is so big that you have a few times mega years, you know. So you can see in other examples also 20, 30 mega years for the lows, while a few mega years for the new phase, and it's comparable to what we see. There is no much precision in this that we can distinguish between smaller and giants. But yeah, I think what can make the difference is this fraction where I see a GPS that is very young, and you can compare it with the mega years structure. Maybe this can give us more indication, even more indication, yeah. More extreme, let's say, a more extreme interval in the life cycle.
Okay. And about the radio power or the jet power, let's say, did you try to infer the kinetic power from the extended emission in these giant radio galaxies and compare that with other kinetic power from other radio galaxies?
No, not yet, not yet. It would be interesting to do that. We measure the radio power by the flux, but not by the kinetics.
The kinetic.
But do you need a speed to do that, or you can just estimate?
No, there are some work I can point to you. Just I don't know. I think they are more empirical. The conversion from the extended, implying that the kinetic power is that what it has blown this cavity, and they have generated these extended radio emissions. So usually estimating the luminosity at this low frequency from extended radio emission, you can.
Sure, there are some interesting works by Ubertosi, for example, studying these cavities in X-rays and trying to spot. Awesome. So you can try to understand the problem by different point of view. Also, the X-ray can give you, Chandra images can give you an indication of previous activity, energetics. It's very complex,
Yeah, exactly. Since these sources have also X-ray data, right? You're studying. So okay. Yeah, exactly. Okay, I see that Felix has a question.
Yes. Thank you, Gabriele. It was very interesting. I'm curious more about this, about the high energy part that I wasn't so familiar with it. So at the beginning, you said that about like 1% or so of radio galaxies are detected in gamma rays, right?
Yeah.
And as you've said, the model for proton emission from the lobes is a little bit puzzling if you think how to get the protons there. But then again, if it's actually inverse Compton by upscattered CMB photons, then should it be much more ubiquitous to see gamma rays from any of these sources, like radio galaxies or giant radio galaxies or other misaligned AGN? Shouldn't there be more detections then of this?
Yeah, it should be more common. Let's say what I concluded together with Persic, that this is very nice modeling, was that to see more of them, you will need super Fermi. Okay, so you will need a Fermi telescope 10 times more sensitive. And in this case, you will see more of these objects. But with the detection threshold that you have now, you can see only the most nearby one. And this gives you only the detection that we got. I mean, there is, of course, Centaurus A for next A, and there are others that I found. But what happens is that as soon as you get far enough from us, you cannot resolve anymore the gamma ray emission, determining which one comes from the lobes and which one comes from the core. So to do that, you need this complex modeling. Probably, if we repeat this modeling on other radio galaxy, we can conclude that also in other cases, much more of the emission comes from these lobes. But yeah, we need more data. Yeah, I agree that there should be more of these objects. And sometimes, if you look at the Fermi catalogs, there is always a fraction of misaligned AGN, but sometimes, since it's not so convincing that they can produce gamma ray, they don't really say, okay, this is a radio galaxy. They just say it's probably a misaligned AGN because there is no indication of a blazar, but leaves the question open. So a detailed study of these sources, I guess, will result in more Fermi radio galaxy than what we believe so far. Yeah, definitely.
Okay, so it's more like a sensitivity issue. Although I would think probably one could one differentiate between lobe emission and core emission just based on how the spectrum looks like, instead of just having, if you don't have the resolution, which is probably not the case.
Yeah, indeed.
Okay, thank you.
Yanis?
Yeah, hi Gabriele.
Hi, Yanni.
Sorry if I missed this, but picture A is not in your sample, right? You're not looking at it.
No.
Would you like to add it? So the reason I'm saying that we have now a long observation, it's a 2 megasecond observation with XP targeting the lobes, well, the lobe. And there are some tentative evidence that we actually see polarization, which would either mean that you have a synchrotron component, a new synchrotron component from electrons, or you have some proton process or something like that. It's not, we only have half the data so far. So it's only 1 megasecond, and there is already a paper out that's claiming things that we cannot really reproduce. So it's not, take that with a grain of salt, but the observation should be done by the end of the year. We should know much better.
Yeah, interesting. Yeah, thanks for the information. I can definitely check what can be done with Picture A. I guess there are many works already, but we can try to reproduce this modeling maybe and see what is possible to do. Yeah.
Yeah, and the XP data are all publicly available too.
Okay.
Okay. If there are no more questions that I don't see, then thank you very much, Gabriele, again.
Grazie. Thank you very much for the invitation. Hope to visit you in person at some point.
Sure, you're welcome. Ok, grazie di nuovo. See you,
Bye,
everyone. Bye.
Bye.
Thank you. Bye, Gabriele.